On behalf of Sonosco, it's my pleasure to welcome you to our 12th webinar about asset integrity management. My name is Marcel Smidia. I'm a co-founder of Sonosco, and I will be facilitating this webinar today. And today we're going to share some practical insights into test procedures, FMEA, and SIF-proof test coverage. Let me start by introducing our guests of today. We've invited two industry experts who will discuss these insights. It's Adolfo Lopez Galvan and Peter Poldervaart. Adolfo is a chemical engineer with over 10 years of experience in safety engineering, and he has specialized in tasks related to IMSIS, such as serving as a chairman for HAZOP and LOPA workshops, conducting SIF design activities, and has earned a functional safety engineer certification from TÜV Rijnland for safety instrumented systems. Peter has more than 10 years of experience as a functional safety engineer working for Shell Projects and Technology before joining Sonosco in 2021. For most of his time, he worked as a LOPA chair and as a SIS lifecycle consultant in projects and training programs within Shell and partners to Shell. Currently, Peter is the IMSIS SIF Pro domain expert and tool trainer in Sonosco. So before we start, let me just outline the framework of our discussion today. We will start by exploring what a test coverage factor is and how it affects SIF PFD calculations. When we have a better understanding of this, we will look into how SIF-proof test coverage factors can be determined from failure mode effect analysis. At the end, we will have some time to answer your questions. We have already received a few up front, but please feel free to put any questions that you may have in the chat. And also, please note that if for any reason you experience a bad connection on your side, a refresh of your browser will bring you back into the webinar. So let's get started. Hi, Adolfo. Nice to have you. How are you today?
Hi, Marcel. Hi, all participants. I'm doing well, thank you.
Thanks. Hi, Peter. How are you doing?
Hey, Marcel. I'm doing good, thank you. Nice to be here.
Well, good to have you both. So let's get started with you, Peter. We've promised to discuss some practical insights into test procedures, FMEA, and SIF-proof test coverage. Can you share some of these insights with us?
Yeah, of course, Marcel. So as most of our audience will know, in the SIF design verification step, the average probability of failure on demand of SIF hardware design is calculated and held against the target PFD of the SIF. The aim of these calculations is to demonstrate whether the average probability of failure on demand of the hardware design can actually achieve the SIF target PFD. So in SIF design verification calculations, one of the factors that influences the outcome of the calculated average probability of failure is the test coverage factor that has been used in those SIF design verification calculations. With most projects that I've worked on in the past, these test coverage factors had to be assumed in the design phase of the project still, as the SIF-proof test procedures were not developed yet at that stage of the project. So there is nothing wrong with that. Yeah, don't get me wrong, nothing wrong with making that assumption. But projects and operating companies have to keep in mind that before commissioning of the project starts, these SIF-proof test procedures must have been developed and must have been checked whether they can achieve the test coverage factor that has been used in the SIF design verification calculations on the project.
I'm sure that everybody in our audience who is a functional safety engineer understands what you just said, but as I'm not a functional safety engineer, can you explain the concept of test coverage factors to me?
Yeah, of course, Marcel. I always like to use the car analogy for this. Although it's a bit crude, it will serve the purpose, I think, for this example. So if you have a yearly checkup of your car in the garage, for example, what they actually do there is check whether the preventive and mitigative barriers that are built into your car still operate as intended, and that there are no unrevealed failures of those built-in safety features that could make driving your car unsafe for you and your family. So the garage would check, for example, the seat belts, the brakes, lights, loop oil level, tires, direction indications, and so on. So with that example, let's assume that in all, the garage mechanic will check and test 9 different safety related features that are designed to prevent harm to you as the car driver in case of an abnormality occurring when you're driving your car. And let's also assume that there are in total 10 different safety features built into the design of your car in total. So the garage mechanic will then test 9 of them. But there is one safety feature that the garage mechanic, for example, cannot test in the garage. You can then basically say that after testing 9 out of the 10 safety features in your car, that the test coverage factor of that yearly checkup, testing 9 out of 10 different safety-related features and hidden failures of those features, has a test coverage factor of 90%.
Okay, so I understand if the garage mechanic will be testing less than all of those 10 built-in safety-related features, the test coverage factor would be always less than 100%.
Yeah, correct. So if we use that in an extreme example, such as the garage mechanic only checking for revealed failures on your brakes and your tires, but not all the other ones, such as your seat belts and lube oil, for example. If he only checks for 2 during the yearly checkup, the test coverage factor of that yearly checkup would only be 20%. So if we put that into safety, functional safety terminology, then you could basically say that the test coverage factor in percentages of a SIF proof test is a measure of how many of the potential unrevealed failures that could prevent the SIF from executing its safety mission when a demand occurs are tested and checked as part of that SIF proof test procedure.
Yeah, clear. But what I'm still not sure of is why the test coverage factors used in design verification must line up with the test coverage factors of the SIF proof test procedures, as you stated before.
So during SIF design verification, the object is to demonstrate that the SIF hardware design can achieve the target PFD as set by the safety integrity level, or SIL as we know it. And as I mentioned before, there are several factors that influence the outcome of the SIF achieved PFD. One of them is the SIF hardware design itself, such as 1 out of 1 or 1 out of 2 sensor configurations, where 1 out of 2 sensor configurations are safer and generally lead to lower achieved PFDs in the calculations. Secondly, is the type of sensor, such as a vortex flow meter or a differential pressure flow meter. That can also influence the equipment failure rate that is used in the calculations, and therefore also influences the achieved PFD of the calculations. The third one is the equipment testing interval that is used in the calculations for the achieved PFD. And typically, we see that more frequent testing also leads to a lower achieved PFD. And the fourth factor that can influence the calculated achieved PFD is the test coverage factor that you are using to calculate the achieved PFD, where basically a higher test coverage factor used in the calculations for the achieved PFD also leads to a lower achieved PFD.
Okay, so that means if you assume a too optimistic test coverage factor in your calculations, the achieved PFD of those calculations may be too optimistic too.
Yeah, that's right. The calculations you made may show that your calculated achieved PFD is less than the target PFD in the software that you use, but in reality, you might PFD using this picture on the next slide. So if we can put on the next slide, yeah. So in the left picture, we can see what the effect of the average PFD of a SIF is with perfect testing. So that's on the left picture. So perfect testing, or in other words, testing with a test procedure that has a test coverage factor of 100%. Over time, the red line, the PFD, as shown by the red line, increases until the perfect proof test with 100% test coverage factor is done. The PFD then resets back to 0 again. And from there on, yes, we go back up again until the test is done. And then when the test is done, it resets back to 0 again. So the PFD average will be, from the calculations, will be the median of the PFD between every test executed as indicated by the green line on the left picture. In the right picture, we can see what the effect of the PFD average is with imperfect testing, or in other words, testing with a test procedure that has a test coverage factor of less than 100%, which is the case for the vast majority of SIF proof test procedures used on production sites, by the way. So again, over time, the PFD, as shown by the red line in the right picture, increases until the imperfect proof test with a test coverage factor of, let's say, 95% is done. The PFD then resets to 0.005 instead of 0, as indicated in the left picture. So a small fraction of the dangerous failures that are not tested for, and the probability of those dangerous failures leading to a failure on demand over time actually accumulates. And this can be seen in the ascending trend of the red line over time. The PFD average, as a result, will be higher with imperfect testing than with perfect testing, as indicated by the green line.
Yeah, and that's a risk, right?
Yes, this may indeed pose a risk, because if the test coverage factor claimed in the calculations is higher than the test coverage factor of the actual test procedure used in the field, the real PFD average of a SIF will actually be higher than what was calculated before in the software. And in the worst case, the real PFD average may even exceed the target PFD of a SIF, which would mean that the overall risk of the scenario that the SIF is protecting against has moved into the intolerable region.
Okay, but there must be something our customers can do to resolve this, right?
Yes, there is. For example, doing more frequent SIF proof testing will reduce the average PFD of the SIF or the SIF element, as I will try to illustrate in this next picture. So if we can put on the next picture, then we see in the left picture, you see an example of a SIF sensor that is tested once every 5 years with a proof test procedure that has a test coverage factor of 95%. Again, over time, the PFD, as shown by the red line, increases until the imperfect proof test with a test coverage factor of, let's say, 95% again is done. And then the PFD resets after the test to around 0.01 instead of 0, as in the previous picture that we've seen with perfect testing. So again, over here, a small fraction of the dangerous failures is not tested for, and the probability of those dangerous failures leading to a failure on demand over time accumulates, which is again shown as the ascending trend of the red line over time. If we compare that to the previous example that we've seen, and as shown again on the right, the previous example with 2-year testing, you can see that the PFD average sits a lot higher in that graph of the 5-yearly testing than for the 2-yearly testing. So in conclusion, more frequent proof testing leads to a lower PFD average. And this is, of course, assuming that both tests have the same test coverage factors, as we want to compare apples to apples, of course. So I would like to note, looking at these two graphs over here, I would like to note, though, that in these example graphs shown in this webinar, we used a device lifetime of 20 years. And this is because a device lifetime of 20 years is also used in the PFDavg calculations in our SIF Pro and IMSys software. So that's why they're all like that with 20 years.
Yeah, okay. I see how more frequent testing can improve the PFDavg, but I know that production units typically do not like frequent testing because of the risk of process upsets, right?
Yeah, you're right. You're right there, Marcel. Most production units would like to stretch their SIF proof test intervals to match the turnaround interval of a production unit for those exact reasons that you just mentioned. Yeah. So then it comes down to adding additional hardware in the design to improve the PFDavg of a SIF, and that is often difficult and expensive in brownfield designs. So the alternative is that you can also improve the test coverage factor of your test procedures. And that basically brings us back to the core question again. What is the test coverage factor used in the SIF testing interval calculations? And what is the test coverage factor of the SIF proof test procedures used in the field? So do they actually line up nicely together? Do they not line up at all? Yeah, so they're completely different. Or maybe you just don't know what the test coverage factor of your proof test procedures in the field are. And what I found in my work over the past years on different production sites is that it is often the latter. We just did not know. Quite a few of the production sites where I worked were not in control of this aspect of functional safety management.
Okay. Adolfo, you've worked on many projects as a functional safety engineer. What is your experience on this topic?
Thank you, Marcel. My experience is much the same. Working on projects, I have found that proof test procedures for SIF components are developed, or when they are available, they are taken from equipment vendor documentation. However, it was often not clear what the test coverage factor of those procedures was, or even it was not clear whether the value matched to the test coverage factor used in the SIF PFD calculations. So let's say, in other words, that it was not clear how accurate the test coverage factor using SIF probability of failure on demand calculation was.
Okay, so how would you resolve this gap then on the project you worked on?
We would solve this gap by performing a failure modes and effects analysis, so also called an FMEA, for all the components of the safety instrumented functions.
Okay. Can you explain to us what a failure mode and effect analysis is?
Yes, of course. A failure modes and effects analysis is similar to a HACCP study, but where instead of investigating what can go wrong in a process facility, this study focuses on identifying failure modes of each component, their causes, and also the effects of these failures. So in the context of a safety instrumented function, this would mean to identify all the relevant failure modes in a transmitter or a valve that can prevent that transmitter or that valve from achieving its safety mission when a demand is placed on the SIF. All these failures are referred also as the dangerous failures of the component. So the FMEA study is typically carried out by a team of specialists from multiple disciplines, a multidisciplinary team, including specialists from instrumentation, maintenance, and other disciplines as well. They all are led by a facilitator, that is the one that conducts the sessions, the meetings. And then there's also a scribe who registers all the findings in the FMEA tables or worksheets.
Yeah. Could you provide some examples of dangerous failure modes of a SIF component used in an FMEA?
Yes, it's important to say that the type of dangerous failure modes could change depending on the type of element. So different components can fail due to different causes, or also it can be said that, to be more clear, that the failure modes are not applicable to all the equipment. So several equipment can have different failure modes, specific ones. So just using again the example of the valve, Some of the dangerous failure modes that could apply to a valve would be fail to close on demand, internal or external leakage, or even structural deficiencies.
Okay. Are there any other types of failures apart from the dangerous failures?
Yes, there are other type of failures apart from dangerous failures. For example, IEC 61508, the part 4 that includes the definitions, divides the failures into dangerous and safe failures. Whilst dangerous failures are the ones that prevent the safety function from operating when required, this safe failure results in the spurious undesired intervention of this safety function. So these safe failures would occur in normal operation, not under a hazardous or situation in the facility, and they would only lead to financial damage. Since they would not affect the SIF intervention of demand, these ones are excluded from the SIF PFD calculation. Then there are other criteria for classifying failures apart from that one. One of them would be to split the failure modes between random and systematic failures. Random failures are exclusive for hardware, and they result from one or more of the possible degradation mechanisms of the component, while systematic failures are applicable both for hardware and software, but they can only be eliminated by modifications in the design or other factors specific of the component.
I see. But how does this help in determining the test coverage factors of the SIF proof test procedures?
Once you complete your FMEA study, you obtain a list of dangerous failures that can occur on the transmitter, the valve, or the SIF component to which you have performed the FMEA. So then you can hold this information against your test procedure to determine whether there is currently in the current procedure a step that would identify these or detect this dangerous failure, or if there is no step in the procedure that would detect this dangerous failure. So when you know from the FMEA study all the dangerous failures that can occur on a transmitter, a valve, or any other component, you can check all the steps in a proof test procedure and then determine which of all these dangerous failure modes will detect it doing the test and then repaired, and which ones will not be detected and will remain there.
Okay, you have a simple example for that?
For example, let's assume an FMEA study carried out for the pressure transmitter we were talking about before. So this study has shown that there are 10 possible and different dangerous failure modes that can prevent the transmitter from achieving the safety mission when required. So we hold these 10 different dangerous failure modes against the proof test procedure of the transmitter. And then it's concluded that 9 of these 10 dangerous failure modes will be detected when performing the test. When I say detected, of course, they would be detected if the failures are actually present in the transmitter when the test is performed. Instead, one of these 10 failures, will not be detected and repaired, so it will remain there. This failure will then be called an undetected dangerous failure. Simplistically, this will give the proof test procedure of this transmitter a test coverage factor of 90%. And this 90%, this value, is the one that should be used in the SIF PFD calculations. I'm deliberately using this word simplistically, as there is more complexity to this that can affect this coverage factor value of the test procedure.
What would that additional complexity be?
Well, I will not go into details of this because it would take too much time, but there are additional complexity due to many and multiple factors that can affect this. So I will give now some examples. For example, I'm focusing still in the pressure transmitter. It could be the transmitter hookup, installation in the field, that this can affect what are the possible dangerous failure modes that would be present in the transmitter. Or, for example, another one could be the service of the transmitter. So the operating service of the transmitter, which is the type and phase of the fluid in the measuring point. For example, if it's a hydrocarbon gas or a liquid, or also the operating conditions, such as the pressure value that is being measured. A third one could be the failure mode weight factoring. The more prevalent dangerous failures on a transmitter will weight heavier than other ones in determining the overall test coverage factor of the proof test. So in other words, at the end for the transmitter or for any other component, there will be dangerous failure modes that will be more critical than others. In all, and as a general conclusion, the FMEA should be set up with a structured approach where information from the field equipment needs to be available, but also the instrumentation, maintenance department, and other related departments should provide their input to the FMEA facilitator. Having all these components, all these elements in the FMEA sessions, this will guarantee to obtain a high quality outputs in the worksheets, which will include an accurate identification of the dangerous failure modes for all the equipment or components under analysis.
We're getting towards the end of our webinar, but before we wrap it up, maybe we can take one more look at what the real world impact is of this, Peter?
Yeah, sure, Marcel. So real world impact, yeah. So as mentioned before in this webinar, worst case is that the test coverage factors used in your instrument testing interval calculations do not line up with the reality. And that with the proof testing that you are doing in the field right now, that this may not be sufficient to achieve the SIF's target PFDs. So as an example of the importance, I can actually give you an example of a company where I worked a couple of years ago, 5 or 6 years ago. And we had a regulator visiting that company after 2 similar incidents with a shutdown valve that didn't close on demand. And it led to a loss of containment scenario in both cases of hydrochlorine in both cases. So it was a health and safety, big risk. And when the regulator came into that company, the first question of the regulator was whether the company was performing periodic proof tests on those valves. And the company answered it, yeah, we were testing it every 4 years, in fact. And then the second question of the regulator was, can you prove to me that every 4 years is frequent enough to achieve the target PFD of the SIF that has failed on demand? And well, as you have heard in this webinar, after this webinar, you will understand that you can only prove that to a regulator if you actually know what your proof test coverage factor is that you have used in the calculations, and what the actual proof test coverage factor is of your proof test procedures that you are using in the field. So without going into too many details of that, and to make that a long story short, the company actually got 6 months from the regulator to get all this sorted out and under control, or potentially face forced closure after those 6 months. So it was quite a big deal, actually, for them not being in control and having these 2 high-risk incidents, Marcel.
Yeah, understand. Adolfo, would you like to say some final words before we wrap it up?
Yes, I mean, from my side, I think I would like to add, and I think it's worth to highlight that for projects, the determination of the test coverage factors for the procedures should not be left until the very end of the project. This topic should be faced at earlier stages, always that is possible. So if this is not handled at an earlier stage of the project, the worst case could mean that the transmitter or the valve, the testing interval calculations have to be redone for these components. And so after making these modifications at the end, the target PFD, the target probability of error on demand of the SIFs cannot be met anymore. At the end, this kind of issue would require design changes in the safety instrumenting function. And these changes will have to be done at a later stage of the project. This type of issues would be a challenging scenario.
Peter, you have anything to add?
Yeah, so actually confirming what and also experiencing what Adolfo just said about late stage project changes and additions. I can relate to that. But also, yeah, so most of what I wanted to say about this subject, I think, was said in this webinar. And I think that for some of our audience today, this crucial element in functional safety management may be a lot to take in and consider. There is a certain level of complexity to it. There is a lot of data to consider in FMEAs and proof test procedures when determining these test coverage factors on projects or production sites. But yeah, so you have to remember, to our audience, you have to remember that, this is a journey to improve your functional safety management process and procedures. It is not something that you can do in a week or in a month. You have to take it one step at a time and work towards perfecting the SIS lifecycle process. That's basically what I want to give, tell as a giveaway for our audience still, Marcel.
Yeah. Okay. Well, thank you both. Let's move on to the questions. I see we received a few. Let me start here. Instead of FMEAs, more and more FMEDAs are advertised. What is the difference, Adolfo?
Well, in a sense, they are the same, with the addition of diagnostic studies in an FMEDA. So hence, the additional D in the FMEDA stands by diagnostics. Some dangerous failures may be detected by the diagnostic in the transmitter, in the valve, in the logic solver, in any SIF component. So these diagnostics can, for example, be located in the transmitter, in the valve, and generate an alarm or a warning to an asset management system. When considering this diagnostic, it is important to look at the effectiveness of the diagnostic, because just generating an alarm, a warning, is not enough. There must be a procedure to ensure that this alarm is taken and there is some action done after this alarm. So I have seen too many cases where there was unfiltered data stream across the screen of an asset management system, leading to be switched off and never look back again. Diagnostics, apart from that, they can also be located in other systems, for example, in the DCS, the distributed control system. You can think of diagnostics such as measuring validation, comparison algorithms, valve stroke time monitoring algorithms. In any case, the same applies. The same that I said before applies also for this type of diagnostics.
Okay. Here's a question. Don't know who can answer this one. Can we use NAMUR NA106 guidance on using PTC values for PFD calculation? Peter, does that ring any bells to you?
No, not to me, or not in that much detail. I'm aware of the NAMUR document, but I wouldn't be able to, with any strong conviction, to make any statement on that. So I think we may have to part that one to maybe answer outside of this webinar, Marcel.
Okay, yeah, that's a good note, Peter. If we do receive any questions that we are not able to answer in this short time frame that we have, obviously we will get back to you. Here's another question. How do we quantify test coverage factors for the tests done in the field? Anybody raising hands?
Yeah, so that's a good question. How do we quantify test coverage factors for the tests done in the field? So basically, that goes through both the FMEA, or FMEDA, or all those methodologies. As Adolfo explained, with an FMEA, you start looking into the details of what could fail in a piece of equipment or a sensor or a valve that could prevent the that element to perform its safety mission when there is a demand. And so the first step is basically by, gathering that information from the relevant disciplines and listing that. And once you know all these failure mechanisms, you can basically look at, if you have to start from scratch, you have to start writing a test procedure with all these different steps and actions, that have to be taken during this test. That basically cover all of these, or preferably all of these, but if not possible, most of these failure modes, that will all be checked then during that test procedure. If you already have a test procedure, once you know all the failure modes that can occur on that piece of equipment, you can look at, okay, what steps do I have currently in my test procedure? And for example, step 2, all right, that tests this failure mode. Step 3 tests this failure mode. So then you can start looking at, what steps cover which failure mode. And then there's a bit more to it. So there's as Adolfo already explained before, weighing factors, because some failures are just more prevalent than others. So there's a bit more complexity to it, and I think Adolfo already said, we're not going to go too much into that, because that would going into the rabbit hole basically. But that's basically, it starts with an FMEA. If you know what failure modes you have, you can start comparing to your test procedures that you have in the field to make that comparison and to see, what do I have and do I need to do more? So I hope that answers basically the question from the audience.
Thanks. Here's another one about increasing the frequency of testing. This person says, if the frequency increased, but still for the same instruments, example, always testing the tires for the car, will it still decrease the PFD average?
Yeah, that's a good question. Let me at least the way I interpret that question. So what the participant is asking, if I test more frequently, will it decrease the PFD average? And the short answer is yes. And the long answer is it could actually. So you will see once you do these PFD calculations, more frequent testing typically helps you in getting the PFD average down, as you've also seen in that trend with the picture that I showed that had the 2-year and the 5-year example. But that only works up to a certain degree. At some point, because testing also means unavailability of your instrument. So when you're testing, that means that at that point in time, your instrument is not available if there is any real demand from the process to perform its trip action. So the more frequently that you test, at some point, let's say in an extreme case, if you start testing once every day, your PFD average calculation will not show a lower PFD anymore, but it will actually show a higher PFD, because in this extreme case where you're testing once every day, you've basically lifted up the unavailability of your instrument dramatically. So this is an extreme example, of course. But so if I understand the question correctly, then yes, more frequent testing does improve the PFD average of your calculations. More frequent testing, assuming, of course, that you're using the same test coverage factors and same equipment, so that you're comparing apples to apples, of course. But too frequent testing, that there will be an inflection point at where basically it doesn't work anymore to do more frequent testing because of the unavailability of your instruments, basically limiting any further progress on PFD average.
Yeah.
Hope that is answering the question properly.
Okay, thanks, Peter. Another question. I think this came while you were answering the FMEDA question, Adolfo. Here's somebody asking, I've heard the term FMECA as well.
Ah.
What is the difference with FMEA?
Well, also here, in a sense, they are the same, but in this case with the addition of criticality analysis in the FMECA. So here, the C stands by criticality. So during the analysis, during the study, it's also perform a criticality analysis. And this is used to quantify the relative magnitude of each failure effect to support decision making. So at this point, this is related with the weighting factor that we were mentioning before for the failure modes and the test coverage factor. That some failures are more critical than others. So
Yeah.
at the end, this criticality would mean the combination of likelihood and severity, and it will establish to this weight factor for each of the dangerous failure modes.
Yeah. It seems like we're missing Peter, but I think I have a question for you, Adolfo.
Mhm.
Is there a reference standard for these FMEA procedures?
Yes, it's the IEC 60812, and this is a procedure that gives some guidance to perform the FMEA. It defines some details about the methodology to follow during the sessions, during the study, and also it provides some templates for the registration worksheets, the FMEA tables.
Okay. Here somebody asks, I have noticed that safe failure data is often made available together with dangerous failure rate data. Is safe failure data used in any kind of calculation at all?
Yes, for an equipment, for a SIF component, for example, together with the dangerous failure data, also the safe failure data is provided. And this is because this data is used for the spurious strip calculation. So this is for obtaining as a final result the spurious strip rate, which is expressed in years. This spurious strip rate, what it does is to measure how often a safety function will activate when not required in the normal operation, in the safe mode that we were mentioning before. And these activations of the SIF would lead to financial damages. These financial damages would be, for example, loss of production because the facility would go in shutdown condition, or delays in the operation due to the restart.
Yeah. Okay. Just another question popped up in the chat, also related, but this to FMEDA, Adolfo. So you again, is it possible to do FMEDA using IMSIS?
So, I mean, for each equipment in IMSIS, there is an FMEA section. And I will ask also, now that I see that Peter is joining, that he adds also his contribution to this. But at the end, there is a section relevant to each equipment in which all these the kind of data is included. It includes all the testing, but it also has columns for diagnostics, the D of FMEA. So the question is, diagnostics can be included.
Did you get that question, Peter? We saw you. You probably had some issues with your connection.
Yeah, correct. So, of course, obviously, always at the wrong time. My VPN dropped out, so I had to re-log in. So hopefully, it didn't interrupt too much. I didn't get the question exactly, but I think Adolfo already answered it, or.
Yeah, I think Adolfo was checking with you if IMSIS also offers possibilities to do FMEDA. That was the question that we got.
Yeah, so not directly in the software itself currently. You cannot like really perform an FMEDA in the software itself. But you can get the information or the results basically from the FMEA or the FMEDA basically as input to your calculations into IMSIS.
Okay, clear. Well, now we have you back, Peter. I have a question here that says we have never inventoried test coverage factors on our side. Do I really need them?
Yeah. So yes, I think the answer to that question has largely been given in this webinar to that participant. So as stated before, worst case is that the test coverage factors that you use in your calculations for determining testing intervals do not line up with the reality, and that with the proof testing that you are doing in the field right now may not be sufficient to achieve the SIF's target PFD. So yeah, worst case is that you have an incident then on site, and that may, if you're not in control of this aspect, as I gave before, this example of this regulator coming to that company and asking questions, so it may lead to further complications basically. So even if you've not inventoried them ever before, it would be a good idea to start thinking about, what do we need to do to put this process in place and see, if we can make that check between real world and basically, assumptions that we made in the calculations. So that would always be a good idea, I think.
Okay. We have a couple of more minutes. Just a question popped up here. For SIF elements in service longer than service life of 20 years, for instance, as used in the tool, how will that affect the PFD average, assuming the test frequency remain unchanged?
So that's a good question, and that brings us back a little bit to some of our participants may also be familiar with that. That brings us back to the bathtub model, where the failure rates, at least if we're talking about failure rates that we're using in our master tags or our master equipment in SIF Pro and IMSys, is based on basically the baseline of the bathtub model. So a fairly continuous rate of failure rates after commissioning, but before aging issues. So if you keep them longer in service than the device lifetime, or basically the baseline of the bathtub model, and use the same testing intervals, I would be a bit careful and see if you can get some more statistical data on failure rate data on that particular type of equipment or type of instrument that has been in service for more than 20 years. Yeah. So does it still follow more or less, that baseline, or does it really shoot all the way up to the top? Because if that is the case, then you will have to do more frequent testing, because the failure rate that you're using in your calculations will not match reality anymore.
Clear. It's time to wrap it up, to close it off for today, because we're at the end of the session. Our time has run out. Thank you for this informative discussion, guys. It's good to have you both, and I think we had a few nice questions. Again, if we didn't answer all of them, we will get back to them. So for all of you viewers, thank you for joining. Good to see you again, and hope you join again soon. Please take note that this webinar will soon be available as a download from our website. So you can always download it and look at it again. And then before I close off, I would like to mention that we are already planning the next IMS webinars. First, there will be a webinar, an introduction to the Synosco Academy. That's a portal for our clients offering online IMS tool training. That will be October the 5th. And then we're still preparing the details for the following two. But on the 17th of October, there will be an IMS software-focused webinar. And in November, the 7th, there will be a webinar specifically on the RCM methodology. So that was it for today. Thank you all for joining, and hope to see you back soon. Thank you.
Thank you all.
Thank you.
Thank you. Bye-bye.
Bye.